Hello and welcome to week 9 of this course on big data. In this course, we will spend the time on understanding machine learning at massive scale, specifically using the libraries that are part of the MLlib module of Spark. My name is Rangarajan, and I'll be your instructor for this week. So let's begin by understanding a bit about what makes big data special when it comes to machine learning. We spoke a bit about what makes big data special when it comes to data science more broadly, and that was done as part of week one's lectures. So we specifically summarized it as the tooling changes, but the motivations do not change. So in this specific case, when machine learning is involved, which is but a branch of data science, what changes here is again tooling, but the nature of the tool that is required in order for machine learning problems to be solved is actually quite different from just data science or statistics or any other type of business analytics. So first and foremost, let's spend some time understanding what makes machine learning complicated, and then we'll talk about how you could look to solve for large scale machine learning if all you had is just access to a single machine, and then we will graduate to a cluster, like how we work with Spark. First and foremost, it's important to understand what makes machine learning complex compared to, let's say, statistics, is the fact that there is a lot of interconnections between different parts of the data on which the learning is happening. And those interconnections are represented using various formulations or representations, be it linear, be it non-linear, be it through neural networks or any other form of uh, capacity that these models would have, or these algorithms have. So at the end of the day, these representations all require the ability to exchange information between various portions of the learning, and therefore um, if adequate amount of information is exchanged, then the capacity is optimally utilized, and you make progress in learning about the pattern and force fitting a curve to the underlying data sets that are presented to the machine learning. So this information exchange becomes the key on which you have to optimize when the data becomes very large in scale. Because ultimately, what you're trying to do is find patterns that explain how that large a data set can be generated or is generated using some kind of a phenomenon. So the constraints around large data sets are really constraints around information exchange. So let's make some assumptions about what those constraints can be manifested as, and then you start to get problems, rather, you start to get solutions to your problems. So first and foremost, let's simplify. Let's think about how you can solve for big data just using a single machine. So this single machine is typically, for instance, your laptop or your desktop or a server that's available to you. The server in practice might be having multiple chips, multiple cores, CPU cores, and then usually it has some finite RAM, and then a set of hard disks on which the data is present. So for the purposes of this exercise or this discussion, let's assume that storage is separate, which means you're not really constrained by the data that's available in that machine, rather the storage space available in that machine. You're able to store very large data sets. Or alternatively, let's imagine that that machine has the hard disk space that's able to store terabytes of data. So the storage of big data itself is not a problem, but the fact that machine learning needs this information exchange about the representations of the model means that you're constrained by how much the CPU is able to process at any point in time, specifically how much RAM is available for the CPUs to do the processing. In a typical machine that's modern, you would have multiple cores. So each core could be doing its own thing or not based on how much you leverage the parallelism within that machine. But more importantly, even if you choose to use just one core or multiple cores, all information exchange that needs to happen for the ML to make progress is via the RAM, which is the memory. So in this kind of a constraint, rather in this kind of a setting, the constraint that is imposed is something called as the shared memory execution, which means the CPU cores that are part of that single machine are able to share information amongst each other using a shared memory construct, which is basically the RAM in that machine, and then they're able to make progress and learn patterns, right, in a way that's distributed, in a way that's parallelized. If you didn't have multiple cores, if you just had one core, the same um, constraint is applicable. It's just that you would use the memory as your store for making, making calls to retrieve data and also to store data for that particular ML execution. Now, what this shared memory execution model also means is you really cannot think about sharing memory which is belonging to a different machine. And that comes back to the fact that latencies, the moment you go across machines over the network, is in the order of milliseconds, at least for typical network connections. And we took a look at this earlier on in one of the week one or week two lectures. Whereas the latencies within a machine between the CPU to the RAM is in the order of nanoseconds. So this millisecond latency boundary uh, practically prevents, any kind of shared memory execution model to cut across machines, right? It's usually restricted to a single machine. Now, why is this important? Why is this discussion important? It's because the underlying algorithm, which is what you're training, the ML algorithm, could or could not be making this kind of a assumption when it runs. So let's take a look at uh, approaches that existed for solving for machine learning on big data when it comes to a single machine or when it comes to algorithms which are tuned towards shared memory execution models. First and foremost, um, there are many pipelines which are capable of utilizing all the cores in a single machine. So those are called as multi-core optimization libraries, and some of the common Python-based libraries are Dask and Numba. So Dask is actually a very popular add-on to the base Python libraries of NumPy and Pandas, etc. The purpose of Dask is to take single core Python applications and execute them scalably, utilizing all the cores in that single machine. Fundamentally, that is hinged on a shared memory model in terms of execution, which means it works great when all the cores are decided on a single machine. But the moment you go across the network, it doesn't work because the latencies will kill it, and it could time out. It could result in errors which are unexplainable, etc. So task is meant for a single machine execution. It's a very good option. Numba is also there, or number, how you pronounce it. But this is basically looking at linear algebra primitives which exist within NumPy and takes it and executes it across like CPUs or GPUs, as the case may be, whatever is available in that machine. So again, you can solve for very large data set computations in an efficient and parallelized manner by leveraging the CPUs and the GPUs within that single machine. The other way to solve for this is to limit the amount of memory because if the constraint is about information exchange through a shared memory, then the amount of information you can pump through could become more if you limit the size of the data in memory. And that's possible if you use optimized data formats. So, for instance, you could take a data set which is representing categorical variables and you want to, let's say, train a classification model on top of it. Instead of continuing with the representation of the data as categorical variables, which is basically as key, you could take that data and convert it into binary and have more efficient representations of the same data, such that the memory footprint of the data is lesser. So, in this kind of a setup, you would be able to squeeze more into the same RAM. The other example here is use formats which are geared towards allowing you to read only the data set that you really need. So one such example is called as Parquet. These are what's more generally these are called as columnar data formats. So imagine you have a data set which has got 100 columns, and the data set is, let's say, 1 terabyte in size, and you have the hard disk in that machine to be able to store 1 terabyte. But then when you read data, since every read from the operating system goes to the file system cache, which is basically memory again, there is pressure on how much memory you can really use for your computations on ML algorithms, right? If you didn't have Parquet storage, if you just had the 1 terabyte stored as a CSV or something like that, you need to read all of that 1 terabyte into the RAM. At some point, rather, you'll read it in phases, but you will read basically all the columns of every single row before making your way through to specific columns that you may be requiring. Let's assume that the model really learns only on 10 columns instead of all the 100. Then, because you're forced to read all of the 100 columns due to the format of the data being CSV, you're not really optimizing for the specific workload that you really need only 10 columns. Whereas in the columnar-based storage, the data set is stored in the disk in such a way that allows for efficient retrieval of only the columns that you're interested in, so that the rest of the columns are not even picked up. So in this case, 10% of your data is what you need. So 10% of 1 terabyte is 100 GB, and you're able to get through 100 GB of data much faster than the 1 terabyte that you'd have had to read otherwise. So that's another example of optimized data format. The third approach, which is the naive approach, I would say, is to just pick up smaller data. Yeah, that's all right. Big data is there, you know it. But then in practice, you might find that actually not all of the data is useful. So the example being clickstream data. In certain use cases, let's just explain clickstream, right? Clickstream is basically when users tap into your website or tap into your mobile app, and they click through various things. They hover their mouse around certain things, and you capture every single such event. And when you capture that and you make it available for analysis, that's basically clickstream analytics. Now, for certain kinds of problem statements, the richness that's there in that kind of a data capture might be too much, right? It might be too much because you are really looking at all kinds of events generated by the user, including the presence of non-events. Non-events meaning I opened a page, but I didn't really click anything. I just didn't even move my mouse. And that could be generating an event because that's useful for providing nudges and so on. But for other kinds of use cases, like let's say fraud use cases, maybe that level of detail on clickstream is not useful. And you're really interested in only certain specific patterns. Or you might have some advertising related use cases, which means you might not really be interested in every single event, and it's okay to randomly start generating uh, nudges so that the advertising is effective. So in any event, some of the ML use cases could be in such a way that you could get away with smaller data. One simple way to, of course, generate smaller data from large data is sampling, and you could use things like stratified sampling and such to make sure that the data is representative of the sample data rather is representative of the base data with respect to the classes that you're trying to classify on or you're trying to build a model on. The second example is sequential batch training. Some ML algorithms are conducive to sequentially update themselves on batches of data trained at a time. Like for instance, neural networks, right? You could just take a look at a bunch of data sets and start applying back propagation and learn the weights, and then read the next batch of data and continue doing that until you're done with the entire batch. So that way, you don't have to deal with processing the entire batch in one go. Rather, processing the entire base data in one go, you just process one batch at a time and you make progress and such that you finish the entire thing. So all of these are different techniques for dealing with large data in a single machine. But what we will see is that a typical ML algorithm, which makes this shared memory execution constraint, is really limited to a single machine where the memory can be shared without latency implications. And therefore, it limits the extent of parallelism, it limits the extent of productivity that you can drive from it. So in the next video, we will start looking at what does ML truly at big data scale mean and how can we solve for it.